Can you hear me? Ok.
Il microfono è solo per la parte di streaming,
Ok.
quindi l'aula è in audio voce.
Ok, allora mi sa che approfitterò dell'acqua. Ok, I am Massimiliano Guarrasi from Cineca. I work in the same group of Fabio Affinito. I'm an astrophysicist, and I worked on the parallel optimization of several codes, particularly on some astrophysical code and on some FFT libraries. Today we will work on Mpi. This presentation can be divided in 4 parts. In the first part of today, we will see we will have an introduction on Mpi, that is the most important library for parallel computing on distributed memory HPC machines. We will see the basic Mpi programs. We will introduce Mpi communicators, point-to-point communication instruction, the difference between blocking and non-blocking message passing operation, and how to avoid the deadlock on your codes. After this first part, I think that we will finish around 10:30 or 11. We will start an extended hands-on on this. Sorry?
Please use the microphone.
What? Oh. Non sente niente.
The microphone is not for audio in this room. It's just for the remote streaming and for the recording. So you must rely on the voice of our
Okay.
teacher.
Probably it's better if we could close this. So, after this first part of the presentation, we will have an hands-on session in which we'll work on some simple codes. And in the afternoon, we will have another presentation about the collective operation in Mpi, and finally another Okay, do you hear me? Ah. Okay. Niente.
Questo è acceso.
Niente. Niente.
Non possiamo neanche fare la voce.
Vabbè, pazienza. Ok, cercherò di fare il mio meglio. Ok, now we can start with this first session. Okay, yesterday you worked on OpenMP, and particularly you have seen how to handling parallel program when you have a shared memory system. Now we will work on mainly on distributed memory system, but the MPI approach can be adapted also on shared memory system because the approach is the same independently from the machine that we have. Generally speaking, MPI was built to work when you have a machine that have several cores distributed on several racks, and each core have its own memory that is divided from the other core or processor of the machine. So in this case, especially if you have a code that needs of boundary condition or something similar to this, you need to pass some information between one core and the others. And in this case, we have to use an instrument to pass this message. Okay. So, unlike using MPI, unlike the shared memory model, our resources are now local. Each processor have his own register, his own memory, his own portion of our data. So each processor works in its own environment. You have the possibility to send message that send some instruction from one processor to another one. For example, you can say to one processor stop, or stop to compute, or simply print some data, or you can pass some information to another processor. As I already told you, this approach can be used both on distributed memory machine that on shared memory architecture, and but you have to understand that since the network between the different processor is limited, the cost of a message passing operation on parallel distributed system is greater than if you have an OpenMP instruction. So you have to manage in a different way the programming of your code. Clearly, this approach have a lot of advantages. For example, if you have a very large parallel machine, or the order of magnitude, for example, of several thousand cores, you can distribute your computational all core of your own machine, and in this case you can greatly speed up your code. The approach is portable in the sense that you can write your code using MPI, and you can port your code on all the machine in the world, because MPI approach is already implemented in all the parallel machine that you can find in the world. MPI library have a long history, and this means that you can find a lot of of example, and you can use this as example to write your own code. And this is another important thing. Clearly, we have also some drawbacks. For example, you can have a lot of error if you not write your code carefully. It probably, it runs. Good.
Now switch on the not delayed output because
Prova. Prova, prova. Ha smesso. Prova. Ok.
If we can enforce your voice, it is better for the
Okay.
the end of it.
Okay. Probably it is easier to have an error with MPI than with OpenMP, but yeah, if you consider that with OpenMP the most you do is to arrive on some tens of cores, whereas if you use MPI you can use 1,000 cores. You can understand that MPI have enormous potential if used well. Clearly, if you want to write a code using MPI, you have to rewrite your code, not only add some instruction as you do with OpenMP. And using MPI, you have a lot of memory overheads, so you have also to manage this issue. But in any case, in my opinion, the most important drawback using MPI is the time spent in message passing. It is quite common that in some codes, when you use too much core, the time spent in message passing operation is greater than the time spent in computation. So you have to find also the limit of your code, and we will see in the following presentation how we can manage also this issue. So, as I already told you, in order to maximize the performance of your code, the program should spend as little time as possible in communication operations. So when you write your code, you have to think how to minimize the communication. And this means that you have to think to minimize the message passing instruction, in the sense that, for example, you can, if you have to pass 1,000 variable, you can pass this variable using 1,000 message, or only a message that contains a vector with all the 1,000 the 1,000 variable. And this means that in the first case, you have to spend time for pass the message, and you spend a lot of time in the latency to start the send operation and the receive operation. So if you want to minimize the message passing, you have to write only one instruction that pass all the data in the same communication. So how we can do a message passing operation? In MPI you have a lot of instruction, but you can synthesize these operations in three types of operation. The first one is the send operation. The other one is the receive operation, and the third one kind of operation that you can perform is the synchronization. We will see in a few minutes how this means send operation, receive operation, and synchronization. Oh, sorry. This is a simple schema of how we proceed. We can imagine to have two nodes. Each node contains, for example, one processor or one process and its own memory. If you want to pass, for example, from the memory of the node A this variable, and we want to pass this information to the second node, prova. C'è un po' di ritardo.
Forse sull'altra uscita è loop.
Prova. Prova. Ok, mentre continuo. Ok, as I already told you, you have to send a message from the first node to the second one using the network that interconnect the two nodes. Clearly, we can have a lot of network. For example, we can use a simple Ethernet connection, but in this case, we spend a lot of time sending messages because the latency and the speed of a simple Ethernet connection is very slow. Or we can have a more evolved network like InfiniBand or Omnipath. In these cases, the computational cost of this send operation is lower because these kind of networks were made to have a very low latency, but in any case the cost is an order of magnitude larger at least than the moving operation inside the memory of your nodes. So you can imagine that a send operation using MPI is 10 times slower than an OpenMP send operation. Okay. And this is a short introduction on MPI standard. MPI is a standard that was defined several years ago, I think in the 90s. And the standard was done by a consortium of organization, and here you can find all the information about the current standard. Particularly, MPI defines some APIs for C and Fortran. The use of C++ is admitted, starting from standard 2.2, but it is not completed as on using C and Fortran, so you have also to handle this. In my experience, all the implementation of MPI handle well also C++, but it is not automatic. Other languages are partially supported. For example, we have also a very interesting implementation of MPI in Python that is called MPI for Python, and it can be used in a lot of situations. For example, I used this library to do some master-slave programs to easily parallelize a code. But in general, if you want to write a parallel code that use well MPI, the only choose you have is to use Fortran or C. The MPI language, the MPI library is implemented using some function and some subroutine. So you have to call this function and this subroutine to use MPI. And the MPI prime goal is to allow efficient implementation and to be portable. So as I already told you, you write your code for your own machine using the standard, and then you can port your code in all the machines in the world, and you can be sure that if you respect the standard, the code runs well also in the other machine. Currently, MPI have a lot of functionality and support also heterogeneous architectures, even if in this case the performance can decrease. For example, if you have a system that have some processor that have a lot of core together with other processors that have only few core but faster, clearly the synchronization between cores is not automatic, and the performance of the code can decrease. In the last implementation of MPI, for example in MPI 2, the parallel I/O was introduced, then, but also the remote memory access, the memory threads, and it was introduced also an object-oriented programming mode. In the MPI 3 standard, also the non-blocking collective was introduced, and also the implementation of remote memory access was improved. So that's it for the standard. Okay, how we can write a program using MPI? When you use MPI, you ideally write a lot of instances of a serial program that communicate each other using a MPI library. For example, you have to use MPI at the beginning of your code to initialize your code. Then you have to manage the MPI environment using some commands. We will see this command in the afternoon. And you have also to terminate the MPI environment at the end of your code. You can also communicate between pairs of processor. For example, the processor A can communicate with processor B, or and we will see in few minutes an example of this kind of communication. But you can communicate also among group of processor. For example, you can pass a message from one single processor to all the other processor of that your code are using, or between a group of processor to another group of processor. And we will see this other approach in the afternoon.
Are you referring to processes, right?
Yes, in MPI you identify the processor with process, with the name of process. You can imagine that you have a processor. Each processor have, for example, 10 cores. Each cores have a process, and this is an MPI process. You can imagine this process as a virtual processor. Okay, so when I say process or processor, in many cases it is the same.
And it refers to a single core?
Yes, a single core or a single MPI instance. Because using MPI you can also use more MPI process per single core if your architecture can manage it. For example, such an example, in the KNL processor you can launch up to 4 processes per cores. And so if you want to launch a run on using MPI on a KNL that have 68 cores, you can launch up to 68 times 4 MPI process.
Could you go more in depth about this regarding the option to run multiple threads on a single core in this kind of processor, which is not so diffused among the users?
Okay. Generally speaking,
two threads in a core. Instead, you mentioned this KNL processor, which allows 4 threads on a single core.
In my experience, in a lot of cases, for task per core is not so efficient. In my experience, only 1 of 2 codes have an effective advantages from the use of 4 tasks per core. In general, it depends of how it is written, your code, what kind of operation your code do. For example, if your code do computation and after communication, but the communication does not imply synchronization, in this case the use of 4 core is still efficient, but in a large part of the code you have also synchronization operation to handle, and in this case, at least for KNL, you can use at most 2 tasks per core. It is different, for example, in the Power 8 processor. In the Power 8 processor, the multiple task per core is handled in a better way. Okay, yes?
Is there a general way to measure the efficiency, the MPI efficiency of a code?
Yes, try. You have to test your code using, for example, only 1 core, 2, 4, and so on. until you reach the limit of your code. Yeah, you have to do a sort of scaling plot and measure the efficiency of your code that can be measured as time to solution using Mcore divided, time to solution using n cores multiplied by the number of core and divided by the time to solution using one single core. This is the parallel efficiency of your code. In general, you can say that the efficiency is good when this ratio is greater than 0.7 or something like similar. So the only method is to test your code until you reach the limit. But in general, the limit depends also on the array you are using. For example, if you are using a very small array, clearly you compute only few operations and a lot of communication. If you have a large array, probably your code run well also using more core. So you have to repeat the test at least for the size of the computational domain you want to use. Okay, as I already told you, when you write your MPI code, you repeat the same code on all the on all the process you have. The code is the same, and the difference is only that the code works on the portion of your memory, on different portion of the memory of your problem. For example, the most simple example is imagine to have an array of 1,000 times 1,000 elements. You can divide this array in small parts. Each part can be associated to a processor, and you can run your code on the single part of your memory, and then you can collect all the information at the end to find the solution of your problem. Okay. Sorry. Okay. Sorry. Clearly, when you do this, for example, if you have some boundary condition, you have to communicate between processor and okay. Okay. In general, you have also to manage some other issue in MPI. The most important one is the standard don't say you anything about the implementation. That is how the vendor that give you the library perform the operation. So there are a lot of difference in the implementation between the various versions of the MPI library. For example, the Intel MPI version of MPI library is very different from OpenMPI version of MPI CH or other version of MPI. In general, at least at Cineca, the most used version of MPI are the Intel MPI 1 and the Open MPI 1. In the case of Intel MPI, this library was already optimized for Intel processors, so probably using this implementation of MPI, you can obtain the best performance for your code, at least on Intel machines. Clearly, the syntax of your code is the same using all this library. The only thing that that changes the low-level implementation, so the use of particular algorithm to perform the message passing operation, how to handle buffer of memory between processor and network, and so on. In some cluster, for example, Galileo and Marconi at Cineca, you can choose all, at least between the first three implementation of MPI, and you can choose the one you prefer. My suggestion is use always Intel MPI if you want to obtain the best performance, but be careful because usually Intel MPI is more generous than the MPI standard. So probably if you do some very small error in writing your code, the code using Intel MPI runs anyway. But when you move your code on another machine that use, for example, OpenMPI library, your code could have some problem. So the Intel MPI library is the best to run the code after the code is ready. But if you are developing your code, probably the best solution is to use, for example, OpenMPI implementation or MPICH to test the code, and then when the code was tested and debugged, pass on Intel MPI.
Is OpenMPI made by the same association that made OpenMP?
The standard is the same for all the library, but the vendor that produced the libraries is different. For example, the Intel MPI was built by Intel. OpenMPI was built from another association, but in any case, all this library respect the standard that is the same for all the implementations. So you can use the same standard and all the library you can see here. The only difference is in the extra that the vendors add to the library. So you can have some commands that are not included in the standard and that runs on Intel but not on OpenMPI. Okay, when you write your code using MPI, you have also to add the information to use MPI in your code, and you can do this using an MPI header that need to be attached at the beginning of your code, and after this, when you finish to write your command, you have to compile the program using a sort of wrapper of the compiler. You cannot compile the code using, for example, Gfortran or GCC. You have to choose. You can use the standard, for example, GCC, and then you have to add in linking and in including part of the compilation a lot of files, a lot of libraries, and so on. And this is the more difficult way. Or you can use a wrapper. In the case of Fortran, for example, you can use Mpi F90 command that wrap the standard Fortran compiler and automatically add all the library that you need and so on. So this is the easiest way to compile your code using an MPI library. More or less all the MPI implementation I know also on the laptop contains a wrapper to MPI. If you, for example, in Ubuntu install MPI, you will also have a wrapper to your compiler that use MPI. In any case, on all our machine, you have always an MPI wrapper to the compilers. After this, you have to run the code on a parallel machine. You have to submit the code using a batch script. And I imagine that you yesterday already have seen the use of a batch script. The batch script on Galileo now is written using Slurm. The slide is wrong here. I mentioned PBS because until the last year we used the PBS, and now we change the scheduler using Slurm. There are also some commands to use to run your code on a parallel machine that need to be included in your batch script, and these commands are, for example, mpi run or mpi exec or srun in the case of Slurm, that are the commands that say to the scheduler that your code have to run in parallel. But we will see how to use this command in the following part of the presentation. Okay, how to compile a code on our systems. First thing, you have to, for example, if you want to use OpenMPI, you have first to load the right module, that in the Galileo case is OpenMPI, and then you have to use the right MPI wrapper to the compiler, for example MPI CC, and then the usual command that you use to compile a code, for example using C. The same thing also using Intel MPI. For the training session today, I recommend to use the Intel MPI, that is easier. And then this is some command to allocate in an interactive way a job. And we will see better how to do this in the following slide and during the training session. And this is our first MPI program. Okay, this is the first program that we can write. I will comment the program both in Fortran and in C, but in order to be fast, I want to know how many of you use Fortran and how many use C. Please raise the hand, Fortran user. Okay, not more. And C user? Good. Okay.
C wins.
C wins. Okay. I will comment in any case both the two approach. Okay. First, in Fortran, you have to write in Fortran and as usual the name of the program. For example, program hello. Then you have to, as I already told you, you have to include another file that add to the code some variable that need to be included to use MPI, and to perform this you can use the include MPI f.h header file. After this you have to declare the variable as usual. You have to initialize the environment with MPI init. And then you can write something, for example, in this case, I simple print hello world. And finally, you have to finalize your program. The same also in C. You have to include also the MPI header, that in the C case is mpi.h. After this, you have also to start your main code, and then inside the main code you have first to initialize the environment, and after the instruction to print something, you have to finalize your environment. How we can read this program? As I already told you, each process that you are using read all the code following the line of the code. So each process inside your job read the name of the program, after include the header, declare the variable, so these variables are declared in all the process that you have. After this, all the process initialize the environment, and then, and this is the most important thing of this program, all process write hello world. So if you launch this command, for example, on 10 cores, the output of this code is hello world written 10 times. Okay, now we can start to describe the command that we have seen in this first program. The first one, the inclusion of the MPI header file. In C, the inclusion is simpler. Include mpi.h. Simpler is the same independently of the version of C, and it is very easy to use. In Fortran, you have to understand what kind of implementation you have. For example, if you are writing a code using Fortran 77 standard, you have to use include mpif.h. If you are using Fortran 90 that already have the use of modules, you can use the command use MPI. On Fortran 2008 that have the MPI 3 standard, you have to use MPI underscore F08. And in my personal experience, in some case, depending on the implementation, can happen that the use of MPI module doesn't run as you want. So in many cases, even if you are using Fortran 90, you have to switch on the old MPI f.h, but this is only for some implementation. I think that, for example, that this issue arises using MPI CH. And in any case, this header file contains the definition of all the MPI constant and the MPI types and function. So you cannot forget to use to include this header file in your MPI program. Please remember that I already said you the 3 version of the include for Fortran are not equivalent, and if you are using the last standard of Fortran, my suggestion is to switch always to MPI underscore F08, because it have a lot of better command and checking of subroutine than the other 2. Okay. Okay, the second command. Generally speaking, when you write an MPI code and you have to call an MPI function or subroutine, the syntax is the same for all the MPI function and subroutine. In general, in C, a large part of MPI instruction are function, so all the MPI function have this syntax MPI underscore and the name of the function, and yeah, whereas in Fortran almost all the MPI instruction are subroutine, so you have to use the call command and then the name of the subroutine that in any case have a name that starts with MPI underscore and then the name of the function. And in any case, for MPI subroutine in Fortran, you also have a variable that is called usually error, that is an integer and contain information about the state of the operation. So if the operation was completed without error, it is 0, and if the function have some error, this is different by 0. Okay, as I told you before, the first MPI command that you have to write in your code is the initialization of the environment, and this is the function for C and for Fortran. As I can see, it is quite easy. Simple MPI init and then the usual syntax for similar function. In Fortran it is easier. It is only MPI init and the error variable to check if MPI environment have some problem or not. In MPI, it is possible to divide the number of processes you have into groups. So this groups is called communicator, and you using this group, this communicator, you can you can cluster your computational domain, for example, or you can cluster your code to specialize your code. For example, processor from 1 to 10 do an operation, processor from 11 to 20 do another operation, and it can be useful in some case, even if it is not the standard approach used with MPI. In general, at least at your level, the only communicator you will use is the MPI word, that is a standard communicator that was already declared by the initialization of your environment, and the MPI common world communicator contains all the process of your that can be used from your job. So you have to remember to use always, at least at the beginning of your code, this communicator to set your environment. We will see how to use this communicator in the following slide. And please remember that all the MPI subroutine or function have to include the communicator argument, because MPI need to know the communicator that are using to perform the operation that you want. Because, for example, if you have two communicators, the two communicators are isolated, and inside the communicator, each processor or each process can be identified by a number, for example, from 0 to 10, for example, if you have 10 process per communicator. So, if you say, I want to perform this operation on processor 0, but if you don't say to MPI if you want to use the communicator A or the communicator B, he cannot identify the right processor to use. So you have to use the right communicator in all the MPI subroutine you will use. Okay. Sorry.
C'è la pausa caffè adesso alle 10.
Ok. Penso che sia il momento giusto. Ok, we can stop for quanto? 5-10 minuti.
At least 20 minutes.
20 minutes.
At least.
Ok. Ok, iniziamo.
I think that after this long break we can restart.
Okay. We have seen how to write the first MPI, our first MPI program. Now the next step is to manage an MPI program. So the first question that we have is how can we know the number of processor that we have? To reply to this question, we can use this command that in Fortran is this MPI common size that give us as an integer the size of your system. So this means that if we use this command, the output of the command is the number of processors that we have in our communicator, that in many cases is MPI common word, that is the main communicator for MPI. This could be very useful because knowing inside the code the number of processors that you have, you can write a more general code. For example, if you write a code and write inside the code the number of processes is 10, that code can run only on 10 processors. If you use this command, you can check the number of processors that you have and then adapt your code to the number of processors that you have. So probably this is the most important command that you have to use in MPI. There are another important okay. 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 Sorry. Common size. Okay. The second important command that we can use is the processor. It is useful to identify the processor rank. What this means? We can imagine that we have a certain number of processors, for example, as usual, 10 processors. And we want to identify with a label each processor that we have. We can put on each processor a number, for example, from 0 to 9. The rank of the processor is this number, and was identified by the communicator. So you can this means that you can use the same label for different processors in different communicator. Inside a communicator, the number that you are using for the rank identify only one processor. The instruction to find the rank of a processor is the MPI common rank command. As usual, this function requires the name of the communicator and then give as an output the rank of the processor. Please remember that when you write a MPI code, each processor read each row of your code. So if inside your code you write this command, and each processor read this command and put inside the variable that is local for each processor the number that identify that processor. So you can use this variable, for example, using an if cycle to identify a certain processor. For example, you can use MPI common rank and identify and put the label on each processor. Then you can write an if instruction, for example, if rank is equal to something, for example 4, do this operation. If it is 5, do another operation, and so on. Okay. Okay.
What about the physical location of the processors?
Okay.
They can be spread out in separated machines?
It depends on the implementation. Usually, almost all the implementation put contiguous processor in with contiguous number, but it is not automatic.
So they try to gather nearby processors by their indices in the same machines, in the same node, more or less, right?
Yes.
So you will not have processor number 5 here and number 6 in another machine far away.
It is possible, but generally speaking, almost all the implementation of MPI, such as, for example, Intel MPI or MPHEH or OpenMPI, put the processor that are in the same node with contiguous number. For example, in KNL, if you have 2 nodes, in the first 68 number are for the first node, and the second 68 for the second node. It is not automatic, but in general, the people that implement MPI are so smart to put the processor contiguously. Okay, and finally, the last important command is MPI finalize. It is used to finalize the environment before to exit from your program. So we have also other program to exit from our MPI environment. For example, we can also use the MPI abort instruction, that is an instruction that exit from your program, terminate all the MPI process that you have, and it is usually used to save exit from your code when you had an MPI error. For example, you can imagine that some error arises in your code in, for example, a message passing. You receive an error from the error variable of the function that you used. At this point, you can continue with the program, but the program had an error, so probably the results are wrong, or exit. To exit, you can use the MPI abort command. Okay, this is the simplest example of an MPI program, of a general MPI program. Generally speaking, all the Mpi program starts with this command. So you have always, for example, this is in Fortran, but it is the same for C. But in any case, you have always to include the header file, always to declare the variable associated with the Mpi commands, always initialize your Mpi environment, and then always check the number of processor and the ID of each process. Then you have to write your parallel code inside the program, and then before to exit, finalize the environment. And this is the same for C. As you can see, the structure is the same. Header, declaration of variable, initialization, number of process in the communicator, and ID of the single processes. Okay, this is a second version of Hello World. If you remember, in the first version of our Hello World code, we only write Hello World from all the processes that we have. In this second version, we add another instruction. As I told you before, we use common rank and common size to check the total number of processor and the ID of the processor. With this parallel instruction, this is parallel because all the process read this instruction and execute this instruction. We print the number of the ID of the process and the total size of the process. So, for example, on 4 processors, our code give this output. For example, Mpi is 1 of a total of 4 processor. My processor is 0 of a total of 4 processor, and so on. You can see that the order is not guaranteed. This means that, and this is quite clear because each processor read the program, but it is quite common that the processor have different speed in the terms of few percentage per process, but all the processes are different. So the faster process will arrive here before the other. So in this case, the process that was faster is the process 1, and so it arrived before here, and it write for first in our output device. Then the processor 0 in this case, then 3, and then 2. Sorry. Okay. It is clear? Is it clear?
Question. In this example, where did you set the number of communicators and the number of processors inside each communicator?
In this case, we are using the Mpi command word that use all the communicator that that are available. So, for example, you are launching your job on 4 processor. In this case, automatically Mpi command word contains 4 processor. In general, if you create another sub-communicator, this communicator contains only less process.
Okay, so Mpi command word is just the set of all processors.
Yes. Okay. Now, at this point, we learned how to write a parallel code using MPI, but in general, we want also to communicate between processors. For example, to exchange boundary condition. The method to do this, it is quite simple. Simply, a process, for example, 0, can send a message to processor 6, and processor 6 have to receive the message from 0. How to write this command using MPI? Using this two command, send and receive. How we can use this two command? First of all, we have, as before, to check the number of process we have and the ID of processor. As I told you before, every MPI command needs to know the communicator you are using. In this case, we are using MPI common word, so we are using the group that contains all the processor that we have. So, what means this, the first command? Simply, the first command say that for example, in this case, if my d is equal 0, that means that the following command is executed only from processor 0, and this command have to send the variable named a to processor 2, the the variable is an MPI real, have a size of 1, we will see in the following with what this means, and with a tag 10, using the communicator MPI common word in this case, and this is as usual the error variable. In this case we are using Fortran, but the syntax for C is almost the same. The only difference is that you haven't the error variable here, but you have a function, and the exit value of the function is your own error variable. At the same time, the processor with label 1 receive the command from the other processor. We will see the syntax in the following slide, but for now we have only to know that in general, when you want to perform a send-receive operation, you have to use this construction. If rank is equal to something, send information. Else if the rank is equal to something other, receive information. The send and receive information have to be coupled together, and using this method you can pass an information from, for example, in this case, processor E to processor J. It is not possible in general to send an information from a processor to another one if all the processors are sending message. So, for example, if I want to send a message to him, for example, him have to be ready to receive the information. If he is doing something other, he cannot receive the information. This is the most frequent bug in an MPI code. That the bug is that you are sending an information, but no one processor can receive the information because it is doing something other. And this is called a deadlock. We will see in the following slide with some example of deadlock. Okay. The message that we can send. Okay. Usually the data that you are sending is exchanging using a buffer. So you have to prepare a buffer that contains your data, and then you have to send this data inside the MPI command. So you have to prepare the variable. You have to know the dimension of the variable you are sending. That is the number of elements you are sending. You have to know the data type you are sending, and you have to remember also that you are writing a program that have some Fortran subroutine and some other C subroutine. The type between C and Fortran are different, so you have to do some casting operation to exchange variable between subroutine written in Fortran and subroutine written in C, but it is not so frequent. Okay. Okay, this is the standard message structure that you can use. The structure can be divided in envelope and body. The envelope contains source, the ID of the source, the ID of the destination, the name of the communicator you are using, and a tag to identify the message operation. The body of the message is the buffer you are using, that is the memory in which is allocated your message. The count that that tell us what is the array dimension of our variable, and the data type for the variable that we want to pass. We have several data types. In particular, we have some basic data type or some derived data type. You can also build your own data type and pass this data type to the other processor. But in general, at least for this course, we will use only standard the basic data type that are the common data type for CF Fortran. You have float variable, double precision float variable. You have also integer, double precision integer, and also complex and logical variable. In general, this is the data type for Fortran. For example, Mpi integer is the corresponding Mpi data type for the integer Fortran type, and so on. You have Mpi real, Mpi double precision, Mpi complex, Mpi double complex, logical, character, and so on. And the same also for C. You have Mpi char, short, int, long, unsigned char, and so on. You have also clearly float double, long double, and byte, and so on. Okay, in order to do a good communication, that is a communication to succeed, first of all, the sender must specify a valid destination rank, and this is very important, as you can imagine. The receiver must specify a valid source rank. The communicator between sender and receiver need to be the same. The tags must match. And the buffer you are using need to be larger enough to contain the variable you are sending. So if you are sending a vector of 10 real elements in the sender and the receiver is only a vector of 5 elements, you lost 5 elements. So you have also to manage this.
Question. Is that fair to use always the common word communicator as a communicator?
And in 90% of the codes that I know, the only communicator that is used is the Mpi Common Word Communicator. But in few code, it happened that we use more than one communicator. But for 99% of the cases, the only communicator you will use is the Mpi Common Word. Another case that can happen is that, for example, you want to send a buffer of 1 million of elements, but clearly the network haven't all the memory needed to pass 1 million of elements. So the program crashes because the network haven't the memory to send all these messages together. Okay. Okay. In a perfect world, all the things goes well, and all the processors are perfectly synchronized. When you send a message, a receiver is ready to receive the message, but in general it is not true. For example, because in the time in which the receiver have to receive the message, it are performing a sending operation or are computing something. Or the same, on the contrary, the receiver is ready, but the sender is not ready. Clearly, in the best case, this means that the receiver or the sender have to wait that the other is ready, and this means that you lost time in synchronization. But in the worst case, and we will see in the following slide this case. For example, all the processors are sending something, so they wait that the other processor is ready, but no one processor are receiving, so all the processors remain appended in the sending operation, and this is the most common deadlock issue. To avoid this case, we can divide our send and receive operation in blocking and non-blocking operation. A send operation returns all after the buffer received the data you are sending. clearly sorry. Clearly the same also for the receive operation. Blocking receive wait that until the message will be received. Okay. Okay. So this is the flowchart, for example, of a blocking operation. You have the processor 1 that send a data and wait until the data was received from the system buffer of processor 2. At this point, the code, the processor 1 can exit from the send operation, and in any case, the receive remain appended until the data will be received from the buffer. This is the syntax of standard send and receive operation, for example, and as you can see, we have Mpi send command. The first variable is the buffer, that is the name of the variable that you are using. The second is the count, that is the number of element of the array that you are using. Clearly, if you are using a single variable or that have only one element, you have to put here 1. The data type, Mpi real, Mpi integer, Mpi complex, and so on. The destination, that is the ID of the processor that have to receive the variable. The tag, that is a label, generally a number 1, 2, 10, 100, that identify this operation. And finally, the communicator. At the same time, the receive operation is as before. The buffer, that is our variable. The size in terms of element of the variable. The data type. The source, for example, if the message is from processor 0 here, and it will be received from processor 1 here. Sorry. Here we have to put 1, and here we have to put 0. The tag and the tag is here and here, and in any case you have to remember that the tag between send and receive have to be the same. And finally, Mpi common, the communicator, that in most cases is Mpi common word. Finally, you have also to put here the status of the operation. That means the message was received, is not received, and so on. Okay. As I told you before, we can divide the message structure in two parts. The first one is the message body, that is buffer, count, and type, and the second one is the message envelope, that is the source, the tag, the communicator, and the status, and eventually, if needed, the error variable to check if it is all okay. In any case, you have to declare the right variable, that is for count, type, and destination an integer. Also for tag, the communicator is a also an integer, but you can put as communicator Mpi common word that it is declared automatically by the header file of Mpi. And for what concerns the status, you have to remember that the variable that contains the status have a size of Mpi status size. So when you declare this variable, you have to use this array size. And finally, the error is again an integer. Okay, this is our first example of a complete code that send and receive something. Okay, we can see together the use of the, sorry, probability is better if we use the C code. As I told you before, the first command is the mpi.h. In order to include mpi.h, in order to include their file, declaration of variable, the status, declaration of the variable that contain the status, declaration of the array that we want to pass. For example, in this case, we want to pass a variable named A that have two elements, initialization, common size, common rank, in order to identify the total number of processor and the ID of process. Then, in our case, for example, we have only two processors that are identified by 0 and 1 clearly. And we write if my ID is equal 0, that means that the following command are executed only by processor 0. The second command, and with the second command we set inside processor 0 the variable A0 to 3 and A1 to 5. Please remember this, that at this point we print a print operation that, for example, print A. For processor 0, the variable are set to 3 and 5. For processor 1, at this point, it is they are equal to 0. Then we perform a send operation. So we send A that have a size of 2. It is an MPI float. We send A to processor 1 using the tag 10, using the communicator Mpi common word. If my ID is 1, that means that we are passing to the other processor. Processor 1, first of all, receive A from that have the same dimension, that is 2. It is here a float. It received this information from processor 0 using the same tag of the send operation, the same communicator, and using this status. After the variable was received, we can print the data, and the data for processor 1 are the same that from processor 0. And then finally we have to finalize your environment using Mpi finalize.
Is the tag arbitrary there? Can I choose any
Yes, you can choose the tag you want. The only important thing is that the two tag matches, and also that if you are sending a lot of message, for example, for processor 1, 3, 5, 7, and so on, the tag need to be different, because if the tag are the same, you risk to pass the message to the wrong processor. So you have always to use a different tag.
And for what could I use the status variable?
The status variable is used to check if the receive operation was already performed or not, but it is useful only when you use non-blocking message passing operation. If the operation we are performing are blocking, the status need to be inserted, but it is not so necessary. Okay. In the case of send and receive routines, these routines return in the flowchart of the code immediately, and they not wait for any communication event to complete. This means that you can send the message and go to the row down. And this means that this is a non-blocking communication. And this is true for all the non-blocking communication. We will see what is the command to perform a non-blocking communication in the next slide.
Excuse me. In the receive routine, when there is no blocking approach, if there is no data available in the buffer, what happens to a processor which is expecting something to be populated in his buffer when it is, for example, not ready because the sending process has not been reached
Yes,
at that point?
this could be a problem, but the status variable can be used to handle this because the status variable changes when the message is received. So you can write in your code, if the message is received, you can do this. If it's not received, you have to wait.
In an asynchronous approach, in this case,
Yes.
with the no blocking system.
Yes, this variable is done for asynchronous approach, but you can use, and probably this is the best way, an non-blocking send and a blocking receive. So the non-blocking send the message and goes on. The receive operation waits for the data. Okay. And as you told before, the non-blocking communication are used mainly to overlap computation and communication, especially for what concerns the send operation. This is the non-blocking version of send and receive. As you can see, the only difference is the I at the beginning of the command. When you read a code where send and receive have this I at the beginning, this means that you are performing a non-blocking send and receive.
Excuse me, another question. So it means that I can use in the same approach which we saw before, if then in the if which sends non-blocking without the I, and instead in receiving the MPI I receive
Can you repeat?
Mixing in the same instruction.
Ah, okay. I understand.
In the upper part, which is if the process is 0.
Yes.
Send with no blocking
yes.
MPI I send, and in the part which receives from the other process the blocking with MPI received.
Yes.
I
Yes.
can mix the two
Yes,
without
problem. And you can also do, for example, if my processor is, my D is 0, I send something to 1, receive something from 1, then if my, we will see this better in the next slide, in any case, if my processor is 1, receive, and then I send. Using this method, I can perform for each processor a send and a receive operation without issue related to the overlapping or miscommunication or deadlock. And this is the quite common approach that you can use to increase the performance of your code and at the same time avoid the deadlocks. In any case, this is my approach, but this is also a suggestion for you. When you write your code, write always your code before with all blocking operation. After your code run in all the situation you can imagine, change the send with the non-blocking send. But when you write your code, before write your code with the send, because the blocking send help you to debug your code. Okay, this is the sorry. This is the kind of variable you can use with the non-blocking send and receive, but they are the same of the blocking send and receive. And finally, if you want to make a check of the operation when you use when you are using a non-blocking send and receive, you can use you can use, for example, this command to say to your code to wait for the finish of a certain operation. For example, if you use this command, you wait that a particular operation that is labeled by this variable is completed, whereas MPI what all say you that all the variable, that MPI have to wait that all the operation included in this array will be completed. And sorry, probably I forgot to show you this. Yeah. In the asynchronous, in the non-blocking send and receive, we have another instruction that need another variable that need to be added to the command. This variable is the request. That is a variable that identify the communication. It is, you can imagine this like has something like the tag, but is quite different. In the send and receive operation, you have to put both the tag and the request. And in general, many programmers use the same number to identify tag and request. So you can use, after you can use this variable to identify the operation you are awaiting. Okay, this is the syntax for Fortran and the syntax for C, but as you can see, the only difference is that these are subroutine and these other two are function. Okay. You can also test the status of a communication using, as before, the value of the variable request. And the command that you have to use to test the status of a given operation is Mpi test. And the syntax is similar to the wait. You have simply to use the variable request, a flag, the status, and the error variable, and the same also for test all. And the status is the output. I forgot to say you that the flag is the output variable. It is a logical variable that is true if the communication identified by the request was completed and false otherwise. And you can use this command, for example, inside an if cycle to check if you can perform some computation that needs, for example, that a given communication was completed. You can simplify your code, for example, using this three key variable, Mpi standard variable, Mpi any source, any tag. You can put this variable inside the send, the receive operation, and this means, for example, if you put the first variable as source in receive command, this command means that the process have to be ready to receive something from one processor. It is not important which is the processor, but in general, an Mpi receive operation that have inside this command as a source wait for receive the first signal, the first information that arrived to it. And the other one, Mpi any tag. If you put this as a tag in a receive operation, for example, you don't need to specify the number of tags. It is not important for the receive command. He receives every message you send, independently from the tag you are using. Okay, I already told you the issue related to the deadlock, and but in general, this is the most common case. You have two processors. Processor 1 initialize the environment, then compute something, then process 0 send to okay, sorry. Okay, no, it's not so clear, but in general, okay, you can imagine that here processor 0 send something to 1, but processor 1 at the same time are sending something to 0. And no one of these two processors are ready to receive anything. In this case, the two processors remained blocked, waiting for the message was received. Clearly, if you use a non-blocking send, the problem can be avoided, and you can pass the send operation and pass to the receive operation that are probably here, and code can be terminated, and as we imagine. This is okay. Sorry. No, I have this example only in Fortran. This is the example of one example of deadlock. I have, as before, two processors, 0 and 1, and inside, as before, I initialize the environment. I have the number of processors that I have, the ID, and in this case, for the processor 0, I put a receive operation. Sorry. Okay, no, deadlock. I have two receive operations, for example, and followed by two send operations for processor 0 and processor 1. In this case, the two processors are waiting to receive something, but no one are sending something. So the computation remain blocked for processor 0 here and for processor 1 here. How to avoid this deadlock?
Inverting the order of the send and receive is the right approach?
Yes, invert the order of the send and receive in one of the two processors. Yes. For example, in this case, I maintain the same order for processor 0 and invert the order on processor 1. And this is quite easy when you have only few processors and few instructions, but it will become harder when you have a lot of communication and a lot of processor, because the approach in this case usually is divide between processor, even processor and odd processor, and in this case you have to check if, for example, if I am an even processor, I send the message and then receive the message. If I am odd processor, I before receive the message and then send.
In this case, the second processor acts as the master of the communication because it's the first that tries to send, right?
Yes. It is not important the
one?
number of processor. Yes. The only important thing is that one send and the other one receive. At least if you are using, as in this case, a blocking operation. Clearly, you can simplify a lot your code using an all-in-one command that is send receive. The send receive command performs both send and receive operation in a synchronous way. So you can, for example, send this variable with this size and this type to this destination, this number of processor, from this processor simply using this command. Clearly, you have to declare in this command send type and receive type, send size and receive size, clearly destination ID and source ID, the tag that need to be declared here and here, the communicator, the status and the error variable. Probably in this command we have some redundancy in the tag, in the size, in the type, but it is the standard. We have to use this. Probably this could be used only one time, but the standard for now tell us that we have to double this command, this instruction. And please remember that the tag need to be the same. The size of the receive buffer and the send buffer have to be the same, and also clearly the type. And using this command, you can simplify a lot your code, because you can.
Can the send and receive buffer be the same?
What?
The send buffer and receive buffer, can they be the same?
I didn't check it, but I think that buffer. Sorry.
Buffer, yeah.
Buffer. Sorry. The buffer need to be the same as. Sorry. The name of the variable. The buffer.
I mean the
No, it's not automatic. For example, you can call this variable A and this other variable B.
yes, but
The only.
A and A.
Yes, it is possible, because you are write variable in different memory allocation. For example, you are the variable of processor 0 is in is different from the variable in processor 1, even if the two variables have the same name.
But in this case, how is decided which one sends and which one receives? Is a matter of race? I mean, if I use the same location to receive and to send, using the send buffer with the same name as the receive buffer, I should know if I'm sending or receiving something. So, who is if the same instruction is used to send and receive? How can I know what happens? Is driven the event by the who performs first the verb to send?
I don't understand.
I mean, you said that we can use the same function to send and
Yes.
also receive
Yes.
with automatic synchronization
Yes.
of the tasks. He said, can I use the same variable as a send buffer and a receive buffer?
Yes.
And you said we are on different process, so it is allowed. There is no
Yes.
overwriting of the information.
Yes.
But I don't know how can I decide which one is sending and which one is receiving?
It is decided here. The first variable you write is the variable that will be sent, and the second variable that you write here is the variable that will be received. So you have, for example, the variable A in processor 0 that was sent to processor 1 and put inside A on processor 1. And you choose which processor send and which processor receive here in putting here the destination ID and the source ID. Another case that can be need to be handled is, for example, if you perform two send-receive operation. For example, the first one from 0 to 1 and the second one from 1 to 0. Also in this case, we haven't any problem because the send-receive command is blocking and synchronous. So before you send from 0 to 1, and only when 1 received the information, 1 can perform the sending operation from 1 to 0. Okay. The send-receive can be useful, for example, if you want to perform a cyclic communication pattern. The most common case is when you have to resolve, for example, a partial differential equation in 1D. You have to pass the boundary condition for each process to the neighbor processor. So, if you have periodic condition, for example, for your system, that is quite common, you have to pass from 0 the right boundary from, for example, from 0 to 1, from 1 to 2, from 2 to 3, but also from 3 to 0. You can perform this kind of operation simply with this simple code. For example, as before, you have to declare the number of processors and the ID of processors. Then, using the ID of processor, you can define the ID of the processor to the right of each processor and the ID of the processor to the left of each processor using this simple operation. For example, if my ID is 0, 0 plus 1, sorry, okay, the left is easy, but in this case the okay, and this is for 0 the results is 1, for 1 the results is clearly 2, and so on until to reach 3. For the left, the situation is different. You have to use MyID minus 1, for example, but for processor 3, you have the problem that, sorry, for processor 0, you have the problem that at the left of 0 you have 3, so you can by hand put here left equal number of processor minus 1, that is in this case 3. Then this is the buffer, and then you can use send receive using the buffer, the dimension of the buffer, the kind of variable, the receive processor, right? We are sending something to write, then the tag, the name of the buffer that send that we are sending, the dimension, the kind, the name of the processor that send the message, the same tag as before, communicator and status. So using right and left only with one command, you can perform the message passing operation for all the process. Is it clear? Yeah, and at this point, will arrive all the processor. All the processor read as value here the number of processor that they have to the right, and here the number of the processor that have to the left. Okay, this is all the kind of send and receive that you can use. The standard the standard send and receive that you can send, that you can use. This is the standard send, and the standard send is blocking for what concerns the send, but not for the receive operation. It sends to the buffer, and after it sends to the buffer, it can do other. It can go on. We have two implementations: the blocking MPI send and non-blocking, that is I send. In this case, it launches the message and then goes on without checking if the receive buffer received the information. The same for receive. We have receive for blocking and e-receive for non-blocking. Then we have the synchronous send, that it is like blocking, but it waits also for the receiver. So the process goes on only when the receive operation is started. And this S send, synchronous send. So we have the two case, blocking and unblocking. We have also buffered send and buffered receive. That is less used, but it sends the message in a buffer in the network, and after this goes on. And it is quite useful as a sort of intermediate solution between the blocking and unblocking, because we have this intermediate buffer, but this command have an issue that is related to the buffer of the network. In some case, can happen that the buffer cannot contain all the information you are sending, especially if you have a lot of processor and a lot of processor are sending at the same time a lot of information. So it can be used in some cases if you send few messages, but it is better not use this command in massive parallel in a massive parallel program. And then you have also the ready send, that is irrespective of whether the receive operation has completed. But in any case, probably in the future you will use only the standard send and receive operation. Okay. These are the final comment of the first part of this presentation. After this, we will start with some simple exercises. And the comment are that MPI is currently the standard if you have a shared memory, distributed memory system, and you want to pass information between one core and another core. MPI use send and receive command to pass, to communicate between processes. The call can be blocking or non-blocking. The non-blocking calls can overlap communication and computation, but need to be handled carefully, because you have to know the data you are using before to use it. And the most common error in an Mpi program is the deadlock. But you can avoid this deadlock using the send-receive operation of the send-receive command, or writing your code in the right way. Sorry? Sorry,
No, sorry, I was reading the title of the next slide.
Ah, sorry. Suggestion. Okay. Okay. Please check capitalization when program in C. Don't forget error variable for Fortran. And don't forget the status variable for receive call, because it could be important. Use Intel MPI, and for Intel MPI use this command to compile in C and not this one, because this one is for GFortran. So, and finally use okay, this is important, but I think that you already know if you repeat the name of the program twice, you overwrite the program and lost all your data. But
Your source code.
Yes, but it could happen, so be careful also for this. And now, please go at this address. The first 6 exercises of the web page are for are simple MPI program and simple MPI send receive operation. You can find here, sorry. Okay, you can find here all the exercise. These exercises are the exercises of the summer school that we had in Cineca every year. And this is a school of 2 weeks that contains a lot of courses about MPI and OpenMP, but also about a lot of other things. In our case, we are interested only to the first exercises. I think that the first, sorry, okay, we arrive only to exercise 9 today. The other exercises are more difficult and speaks about how to write different communicator, different data type, perform MPI I/O, and some other advanced exercise. In the future, if you want to do also these things, you can follow the summer school at Cineca, or simple from our web page, download the PowerPoint and try to understand how, for example, MPI communicators works from the slides, and then test the exercise from 10 to 16. And that's it. I think that we will start with the most simple exercise. You can.
We need the credential to access the GitLab.
No, it is free. You have only to write git clone and then clone all the repository.
I have a question. As far as I know from your slide, when we use MPI, we can achieve parallelization until the processor or core level. Is it also possible to achieve parallelization till the thread level, which could be potentially?
Yes, it is possible. It is possible to write a code that use both MPI and OpenMP together, and this could increase clearly the performance. Unfortunately, we haven't time to match together the two approaches, but one second. If you go here, eventi Cineca, supercalculate computer graphics, English version, and then no, is not yet available, but in general in our web page there are also the page for the Cineca Summer School. In the summer school we have a course about to merge together MPI and OpenMP, and we have an extended training session of 1 day with a very huge example of code that you need to modify to put inside first OpenMP and then MPI. We can try to find the summer school, Cineca Summer. Okay, this is the last summer school course material. You can have access also without login, but in my case I have my login. Okay. OpenMP. Okay, hybrid programming. Mpi plus OpenMP. And if you want, you can send me an email and I will send the slide if you are not able to download it. Or if you want, generally on May we have this school and you can ask to participate to the school.
So the summer school is in May.
We have 3 editions of the school, one in May, another in, I think in June, and another in July. But it depends on the year. I think that in the 2019 the first one is in May and the last one at the end of July. And one edition is for sure in Bologna and another one is in Rome. Okay. For now we can start for the first program. That is quite simple. You have only to write a program that write hello world, I am processor, the number of processor, of a total of the number of processor we are using. If you want, since you need to use, since you need to use also Galileo, probably you have to write your job script. I imagine that you yesterday already wrote a job script for Slurm, but in any case, this is the job script I wrote for the first program, as you can see. It is better, or I have to increase the character? I can try, but I'm not sure. No. No. No, it is impossible to increase, at least with this program. No.
Ecco, ricordo dove che si fa il resize dei caratteri sul punti. Così che punti?
Sì.
Dov'è che faccio quello?
Far più grande?
Se no non vedo dietro.
Un attimo. Prego. So. Facciamo 14-16. Forse meglio.
Facciamo più grande.
Ok. questo. Okay, clearly, if you have issues with the exercise, you can ask.
attendere, è un blocking, e invece vicino un blocking. L'importante è che rimanga lo stesso tag, però funziona il tag, giusto? Ah no, il tag, giusto? Qui però non sai fare una filosofia if, point to point, perché è una cosa, vedo che c'è un nome mi, quindi probabilmente quello è l'esempio serializzato di prima, quindi
Vabbè, in questo caso funziona solo su processori. Comunque, visto che alla fine sono solo dato, va bene per tutte e due questo. In generale bisogna sempre utilizzare l'IF, però la cosa migliore è sempre quella, processori pari, processori
che è quello semplificato.
Oppure col sempre sì, get send sì, così send, che è quello classico.
virale.